Remember, we have a coequalizer. We have, if these involve sets, we're going to have this, well, in general, for any category, coequalizer will have this particular structure. So we'll have an object X and an object Y, and there's going to be two morphisms in parallel between them, and a morphism Q. And the coequalizer structure is such that Q after F is equal to Q after G. And here, capital Q, if X, Y, and Z are sets, capital Q is going to be the set of equivalence classes of these in Y. So the idea here is that, look, if X is a set, if there's any element X, let's consider, and F maps X to a given value Y, G maps X to a given value Y, those two are considered in the same equivalence class, right? So the example I gave is, suppose X is mapped by F to 1, and that same element over here in X little x is mapped by G to 2. 1 and 2 in Y are considered in the same equivalence class, right? But then maybe there's an element over here in X called, should have chosen more artfully, called A, and F maps A to 2, and G maps A to 3. Now, 2 and 3 are considered the same. They're in the same equivalence class. But more than that, what else is in that equivalence class? 2 and 3 are the same. What else is in that equivalence class? 1 is, because we already said 1 and 2 are in the same equivalence. So you get the sense of glued together, right? Like it's 1 is like glued to 2. They're stuck together from then on. And now we know 2 and 3 are stuck together. And oh, lo and behold, 2 is coming with 1, right? It brought friends with it. And so 1, 2, and 3 are all together now. And that's kind of, as I argued, kind of an emergent property. There may not be any one element here, X, A, B, C, whatever, that F maps to 1 and G maps to 3, but that's not the issue. The issue is those two are together because those equivalence classes are the same. And Q might then, if that were the case, and 1, 2, 3 were the only values of Y, Q might be just one value, the one equivalence class that includes 1, 2, 3 from Y. So Mehdi, you were saying that could you take equivalent coequalizers of graphs?
X and Y and Q are some graphs.
Yeah.
And F and G and Q
That's
are
right.
the graph morphism.
I love it. So X, Y, and Q are graphs. F, G, and Q are graph homomorphisms. That's right. Now, it's important to note that if we take the coequalizer, like in CATLAB, in general, if we ask, what's the coequalizer of X, right? If we have X and Y be graphs, we have to specify F and G, right? And we take the coequalizer, it will give us this map Q and this object capital Q, such that this property holds, right? That this property holds. And by the way, Q is guaranteed to be a. Do you remember with an equalizer. Do I have a nice equalizer here? I think I have an equalizer, or there's an equalizer. Do you remember what E had to be a certain property? What is E? I don't show it graphically, but I could. It would involve a hook. What does E have to be? It has to be I'll give you a hint.
Yeah.
E is a subset of X here. E is the subset of X that what holds? For an equalizer, E is the subset of X for which F agrees with G, right? This is like the subset of X such that F of those things equals G of for a given one of those things in E, call it A, F of A equals G of A, right? It's a subset of E that F and G treat the same.
If F overlaps G within the interval 1, 2, then E would be the interval 1, 2.
That's right. But do you remember E had to be, this little E has to be if capital E is a subset of capital X, what does little e have to be? It has to be a monomorphism. It's monic. In other words, it's a monomorphism. Monic means the same thing. It's just a shortening. Monic is like the adjective. Adjective, I think it's an adjective. It's a monic map. Or it's a monomorphism. Is that sort of description? Okay. Q is got to be either epic or split. It's either got to be epic or split epic. It's like the converse because it's just dual. So and that makes sense, right? Because like Q is the equivalence class of these things. So like every one of them goes to some value of Q, right? So for set, this would be, if these are all sets, this would be a surjection. Okay, but what you were saying, Mehdi, is extremely interesting. That here, yes, if you had F and G be graph homomorphisms, and you had X and Y be graphs, what's going to happen is you're going to get out a graph here. It's going to be really cool.
Q is a version of Y. Is it a version of Y, but it's quite compressed?
It's like a version of Y that's right, but it's collapsed in some way that reflects these maps here, right?
Yeah.
It's collapsed in a way such that anything that so F is a graph homomorphism. It's mapping things in graph X to things in graph Y, right? Oh, it's like sticking, like X goes to Y. It's got like mapping some things onto certain nodes in Y to graph Y, right? And it's like some things in X get stuck together in Y or what have you, and then G is going to map that same X to other things in Y, but there's going to be anything that, if there's a piece of X, of graph X, like a given vertex that is mapped by graph homomorphism F to one vertex of Y, graph Y, and mapped by G to a different vertex of graph Y, they're going to be collapsed, right?
Yeah.
And similarly, if an edge in X, graph X, gets mapped into an edge in graph Y between, the appropriate vertices, but G, so that's via F, but G maps that edge to a different edge in Y between those two same. No, I don't know.
It is same.
Um,
Between the vertices is same.
it-
The mapping from the edge is related to the mapping
of the vertices. Yeah, that's right. So it's going to be
Is that
it's gonna delineate. So if this here is an edge from A to B and X, so there's some edge, A to B and X, it's and maybe F maps it, maps A to some edge in graph Y, B to some vertex in graph Y, maps B to some vertex in graph Y, and maps that edge to some edge between those two. And then if G maps A to some vertex in graph Y, and B to some other vertex in graph Y, different from where F mapped them to. But those vertices get merged. And then there's going to be edges between those, right? And where there's going to be edges between them that come from, because it's collapsing down these at Y, it's collapsing down these two vertices on the source side, and two from where A was mapped, and two vertices from where B was mapped. They got mapped down to the same thing, each of them get boom, boom. They get kind of collapsed over what A mapped by F and A mapped by G get collapsed to one vertex and Y. B mapped by X or by F and B mapped by G get collapsed. And then there's going to be some edges between those collapsed things. Some of those come from where F mapped the edge between A and B to, and some come from where G mapped the edge between G mapped A and B to. And I think there's going to be a further, and it's going to merge those edges between the corresponding new nodes in V, like the appropriate nodes, collapsed nodes in V and X, sort of each collapsed pairwise. It's going to map that. It's going to merge those edges because, like, there was some edge between where F mapped A and F mapped B that's now identified with an edge from where G mapped A to G mapped B, and you're going to collapse those edges. So that's going to be a fascinating graph. Really? So yeah, I'd love to see those.
Yeah.
Oh, you write it down. Yeah, that's really cool. Okay, that is incredibly neat. I would love to see it. And the truth is, like we were saying, products of graphs are very restrictive things, right? Like they're very picayune things. Like they require you to get an edge in the result, you have to have an edge in the corresponding things from both of the other two. But like coproducts, code-limit things like coproducts or the pushouts or coequalizers, those give richer things. You get interesting things out that are kind of constricted. And I would love to see that. That sounds really neat. Coequalizers of graphs. Probably there's some really good intuitions you could have for how to use it fruitfully, right? Yeah. So you could also do it for causal loop diagrams, I think. Coequalizers of causal loop diagrams, sort of collapsing things down. There's probably a really good intuition that you can end up having about like how it will shrink it down so you can use it artfully.
Yeah.
And I do want to share with you, that learning category theory has its challenges, but one thing that I love about it is like once you reach a certain level of understanding, there's tremendous intuition that comes with it. But more than that, like these operations, which seem abstract initially, like product or co-product or pull back or push out or co-equalizer, equalizer, any of these things that seem kind of ethereal and kind of, just very abstract, they actually end up being useful gadgets. Like you build things out of them, you construct things out of them that are really useful. They do work for you, and you can like decompose your what you want to accomplish into these things, and boom, you can do something very quickly. You can do something very quickly that otherwise would require a lot of code that's very ad hoc and might have bugs. You can do it as a simple, a composition of operations. And that's what I think CatLab, or by extension CatCoLab, can do. It's like the right building blocks for the job for many things. It's this very high level building blocks to allow you to think more clearly and express it more compactly, more succinctly.
Those CatLab macros for coequalizer.
Oh yeah, CatLab has full support for coequalizer. So you can use coequalizers with graphs with abandon. It's like one line, right? To use a coequalizer. Now, mind you, you have to pass it morphism. Like you have to specify if cap X and cap Y are graphs, right? Then F is going to be a graph homomorphism, right? An AC set transformation and an attribute transformation in CatLab, which you can ask it to visualize. Remember, with graphs, you can like visualize it. I had it up last class, but like it shows like this graph is mapped on in this way to this one. So you can have that, and then you can take the coequalizer and it'll give it to you. It's very beautiful. That would be a lot of fun to play with, man. Okay. Any other questions in our final few minutes here? Okay, it's the last session before a much needed reading week. So remember, I think in the calendar, there's still like a class, like in my calendar for some reason, there's still a class for Monday, but that's not happening. Next week is a break, and a much needed break. I will try to circulate some readings for the following week, as I normally do. Just to let you know where we're going, I'll just note that we are going to be discussing. So we may read it a little bit more in this chapter, but after that, we're going to be discussing. So it turns out, you saw today, abstract simplicial complexes, topology simple. It turns out there's a construct known as growth in deep topology. Okay, and a growth in deep topology is a really amazing thing, like so much growth in deep did. It involves having a topology that's actually a category. It involves a category in a set of in an associated set of coverings, which are morphisms in a category. And basically, instead of having like a post set of open sets and O of X, we're going to have what's called a site, which is going to be a category in some open covering, some covering. And that covering is going to be defined in terms of morphisms. And we're going to be able to map that over. And a lot of the things we're interested, like with intervals particularly, can be specified as growth in deep topologies very nicely. And it's very beautiful. And they're they're basically categories in just a familiar sense. Although we have to specify this set of coverings as more, the morphisms in the category serve as the covering. So it's quite nice, and it will be used in some of the papers we'll look after that. So my plan is to look at that, and then we're going to start going through some papers that are application papers or more specific, so that are things like involving temporal sheaves. We're going to go through the temporal sheaves paper, and we're going to take a look at a paper on sheaves as the canonical data structure for sensor integration to bring together sensor data. And as time allows, we'll may look at some other papers as well. So that's a little bit about where we are going. Okay, that's all we have time for. Thank you, everyone. Have a good break. I will be in on Monday. On Wednesday, I will be at Xiaoyan's convocation. She's convocating, so she's graduating. Perhaps some of my other students who have graduated or who have finished recently will be there. And then on Thursday, so Tuesday is Remembrance Day. Wednesday, I'll be at convocation. And then Thursday and Friday, I have a specialist medical appointment in Calgary. I'm going to be going to an embassy, to a consulate there. So I'll be out of town I'll be out of the office on Wednesday, Thursday, Friday. Yeah. Okay. Great. Thank you. Take care there.